Uh, Hello, welcome to another lecture of electromagnetic field and waves. Um, I'll just spend a couple of minutes recapping what we did last time. So, if you briefly review, last time what we did was that we basically discussed solutions to the wave equation. And what we did was is that we took the wave equations for electric and magnetic fields, and we looked at plane wave and spherical wave solutions. In plane wave solutions, we saw that points of equal phase form a set of planes. And in spherical waves, what we saw was that basically you have wave fronts of equal phase, right? So on and so forth. And another very interesting thing that we saw last time, which is really important for the course, is how the electric and magnetic fields are related, how electric waves and magnetic waves are related to each other. And fundamentally, what we saw was that you, every everything that every function that satisfies Maxwell equations will satisfy the wave equation, but every function that satisfies the wave equation doesn't necessarily satisfy Maxwell equations. Maxwell equations put on further constraints. For example, if you talk in vacuum, then in vacuum del dot E is 0, del dot B is 0, and del cross E and del cross B dictate how E and B are related to one another. So your solutions to the wave equations must satisfy Maxwell equations. And once they start satisfying that, then we see that B and E are always orthogonal to one another, right? So this is a wave and it's a vector, this is a wave and it's a vector, and these two vectors are orthogonal to one another. Moving on, what we want to do today is basically look at the amount of energy which is transported in electromagnetic fields. We will then look at how electromagnetic waves behave inside a dielectric, and then the last thing we'll do is polarization. So, if you go back to a couple of lectures before, you'll remember that we looked at the energy density, and we gave it the symbol U, due to ambient electric and magnetic fields due to a charge distribution. And what we found was that U is equal to 1 over 2 epsilon naught E squared plus 1 over mu naught B squared. And you derived the second factor, I believe, in homework 3 also. Now, this is the general energy density due to ambient electric and magnetic fields. But if you have, let's say, if you have a propagating plane wave, so let's say that you have a propagating plane wave, then we saw last time that the magnitude of the B field of that plane wave, so let's say you have a propagating electric field, then of course alongside that propagating electric field you also have a propagating magnetic field. So that magnetic field, the amplitude of that magnetic field would be 1 over C times the amplitude of the electric field, right? We've done this, which basically means that the amplitude of the square of the B field would be equal to 1 over C squared times the amplitude of the electric field, right? And we know that C, the speed of light, C, is equal to 1 over the square root of mu naught epsilon naught. So that means that the mod of b squared becomes equal to mu naught epsilon naught mod of e squared, right? Now if we let's call this equation 2, and let's call this equation 1. Now if we substitute equation 1 in equation 2, let's see what we get. What happens is that u becomes equal to 1 over 2 of epsilon naught e squared plus 1 over mu naught times mu naught epsilon naught e squared. So this means that u becomes equal to 1 over 2 times 2 epsilon naught e squared, which is equal to epsilon naught e squared, which is equal to epsilon naught e naught squared cosine squared of kz minus omega t. This basically means that my original electric field was just a plane wave. So just to recall, so our E was basically some E naught cosine of kz minus omega t, and we can give it, let's say it's polarized along the x-axis, so let's say this is I hat, something like that, right? So that's a plane wave. So it turns out that u is equal to epsilon naught e squared cosine squared kz minus omega t. And let's actually give this a name, and let's call this equation 3, because we need to come back to this later on. Okay, so let's call this equation 3. But the really cool stuff here is just this, which is that u is equal to epsilon naught e squared. And why is this cool? The reason this is really cool is that, you see, the electric field contribution originally was half epsilon naught e squared. The magnetic field contribution was half 1 over mu naught b squared. But when you add those, what you find is that both the electric field and the magnetic field, they contribute equally in the amount of energy in the electromagnetic field. So even though the magnitude of the B field is 1 over c times the magnitude of the electric field, but the total contribution towards energy is the same. So E and B contribute equally in the energy. This is a really, really interesting and important take-home concept. But now you might wonder that how can something which is 1 over c times smaller than something else contribute the I mean if mod B is 1 over c times mod E, how can they contribute the same amount of energy? Well, the answer simply is that this is a different quantity to this. The magnitude is related as 1 over c, but they contribute towards energy differently, and hence their total contribution is the same, right? So that's the energy density in a plane wave is then epsilon naught e squared. If you write it down as equation 2, it's epsilon naught e naught squared cosine squared kz minus omega t. We'll come back to this later on. Now that we've talked about energy density, if we go back a few lectures, we also talked about the Poynting vector. So we talked about the Poynting vector. And the Poynting vector physically, what it meant was that the Poynting vector was the energy flux density. So this was the energy flux density. The Poynting vector was the amount of energy coming out of a volume. So it was the energy flux density per unit area per unit time. Right, so it was the energy flux density coming out of area per unit area per unit time. And we found in a previous lecture that S is equal to 1 over mu naught times E cross B. Right? So then what is the Poynting vector for monochromatic electromagnetic plane wave? So for, let's say, a monochromatic, for a monochromatic electromagnetic plane wave, monochromatic basically meaning that one frequency या one wavelength, ठीक है, propagating along the z direction, ठीक है, propagating in z. We can write the electric field vector as some vector E naught e to the I of kz minus omega t, ठीक है, and the corresponding magnetic field related through Maxwell equations becomes E naught over c e to the I of kz minus omega t. What is the direction? Well, the direction is some direction perpendicular to both k and so some direction perpendicular to both this k and this E naught, right? Because this is the direction of this electric field and this is the direction of propagation. Right, so the direction then is just, it's the cross product of E hat crossed with Z hat, right? Okay, so these are of course the complex notation formats of the electric and magnetic fields. The physical waves, so the physical waves would always be the real part of these, right? So the physical wave is real part of these. So the real part of the electric field would be E naught cosine of kz minus omega t. And so if you substitute that for both the electric and magnetic fields, what you find is that S becomes equal to epsilon naught E naught squared cosine squared of kz minus omega t. But S also, S go back to this slide. The real part of the electric field vector, of course, would be the direction that is perpendicular to both B and E, and because it's the cross product, right, as we saw over here. So that cross product is just, so that gives you a Z hat dependence, right? So this is the energy flux density per unit area per unit time. Now notice how this is very similar to the expression that we got for U, which is the energy density. So for plane waves, what we get is that S is equal to, the vector S is equal to the speed of light times U times Z hat. Of course, there's nothing special about the Z hat except for the fact that this is the direction we took about for the direction of propagation for a plane wave. And we saw last time that you can basically generalize this to any I hat or any particular direction, right? So there's nothing special about Z hat. So we know that mod S is equal to the speed of light times mod U, right? So let's just think about this. For example, in a time delta t then, so let's say that light passes through some volume A. So in time delta t, light sweeps some volume which is AC delta T, right? So let's say if light passes through some cross-sectional area A, let me just draw a beam of light. Let's say light passes through, right? So the amount of area, the amount of volume which the light sweeps in time delta T is AC delta T. Okay? So the amount of energy transported in this time, the amount of energy transported would be basically the volume, which is AC delta T times the energy density U. Okay? So that's the total energy transported, but S, which is the Poynting vector, we know that this is the energy flux per unit area per unit time. So obviously then it makes sense that S is equal to C U, ठीक है, उसका जो magnitude है. So that's how that makes sense. Now if that's okay, then I basically want to make a conceptual point, which is that let's say you have a green laser, ठीक है? So let's say we have a green laser. And I mentioned laser because the laser is typically a monochromatic light source. So a green laser typically has a wavelength of 532 nanometers, okay? And which corresponds to a frequency of about 10 to the power of 15 hertz. Now imagine this. You have a frequency of 10 to the power 15 hertz, so you have a time period which is of the order of 10 to the power minus 15 seconds. So when green laser or green light hits a wall, the electric field vector, right, the real part of which is proportional to, so as we saw, E is proportional to cosine of omega t. So that basically means that the electric field vector is tracing out a cosine at basically femtosecond time scales, at petahertz frequencies. So this is a very, very quick change. And we saw that U is proportional to cosine squared. We saw that S is proportional to cosine squared. So if you then go about measuring the energy density of the amount of light falling on, let's say, a photodetector or a wall, what you will measure is almost certainly going to be an average measurement of many cycles of that electromagnetic wave, right? If you go around measuring, so it's better to talk about the average energy density of a plane wave. So the average energy density which is something that you're more likely to measure, because you can't measure a wave which is changing at 10 to the power 15 hertz, right? I mean, there are some really ultra fast photonic systems out there, but petahertz is still a challenge, a huge challenge actually. I mean, just to put into perspective, your radio frequency circuits, which are high frequency circuits, typically operate at megahertz, right? And then yes, you have your processors are working at gigahertz. But very few electronics out there can do anything at the terahertz, and this is the petahertz, right? So what you typically measure is average energy density, which is the average over over one time period. So we know that U is proportional to cosine squared of omega t. So the average over one period, the average U becomes equal to the average of cosine squared is a half, so it becomes equal to 1 over 2 epsilon naught E squared, E naught squared. E naught is the magnitude of the electric field. So similarly then, the average Poynting vector which, if we denote it by S, becomes equal to 1 over 2 epsilon naught, this is a C, times E naught squared z hat, right? So it's almost always better to talk in terms of averages when we talk about measurements rather than talking about absolute values. So just to summarize this part then, we've seen that electromagnetic waves, so we've seen how the E and B field are related to one another through Maxwell equations and how there's the solutions of the wave equation. We've seen the amount of energy density in a plane wave. We've seen the Poynting vector of a plane wave. And then we've seen that if you have actual visible light, then the waveform is basically moving around or changing at 10 power minus 15 time scales. So what you almost always see is averages. So the average energy density and the average Poynting vector is half epsilon naught E square. But of course, this is just true for a plane wave, right? So moving on now, what we want to do is to have an idea of how electromagnetic waves are generated and behave inside a medium. So what we're basically talking about here is electromagnetic waves in matter. So far, our discussion in the last lecture and this lecture has been by taking Maxwell equations in vacuum, making wave equations out of that, and then solving those wave equations and looking at the solutions. So all the solutions and plane waves and spherical waves that we've looked at so far have all been the solutions in vacuum. But now the question is that what if we have a dielectric? Now, what do we mean by when we say a dielectric? For example, glass is a dielectric. Something like, let's say, a sheet of plexiglass or acrylic, that'll be a dielectric. A piece of wood would be a dielectric, so on and so forth. So, so what if we have a dielectric and the constraints we have is that whatever material we are looking at, it has no free charges, and this material that we are looking at has no free currents. So we're basically looking at an insulator. So our question is, what happens to electromagnetic waves inside an insulator? Now, if you go back a few lectures before the spring break, you would remember that we looked at what we called the useful Maxwell equations. Right? Inside a medium or any material. And those were basically expressed in terms of the electric displacement and in terms of the H field as we described it. And what you would recall was that so if you have a dielectric, but in this dielectric you don't have any free charges, so on and so forth. So what you get is that del dot D, which is equal to the free charge, where the free charge is 0, del dot D is 0. Similarly, del dot B, well, this is always 0, right? And unless we discover magnetic monopoles. Similarly, del cross E, since we don't have any currents, is just minus partial B by partial T, and del cross H, since we don't have any currents, of course, is partial D by partial T. Right? If you want to go to the derivation of this, you just need to go back a few lectures, and we've described these. Okay. Just to refer to them, I'll just call them. So these are also Maxwell equations, and these are more general Maxwell equations than the ones we did before. But still, of course, we have a constraint: there are no free charges, no free currents, right? But inside a material. The previous version of Maxwell equations which we did, which was del dot E is rho over epsilon naught del dot B is 0. Those are always true. The only difference is that when you have a material such as this, then when you talk about rho in Maxwell equations, rho is like the sum of bound charges, free charges, and displacement charges, right? So you have to add up all of them. So so then if we talk about a linear material, so inside a linear material we know that D is equal to epsilon E and H is equal to 1 over mu B, right? And this is all stuff that we've done before. Now, like I said, you can either use the version of Maxwell equations with the displacement current in the H field, or you can use the version we always use. They are both correct. It's just that one is easier to use than the other, because del dot D is equal to the free charges, del cross H is proportional to the free current, and these are easier quantities to work with than the simple Maxwell equations, right? But they are both correct. I don't want you to be confused by this, right? And this is true for linear dielectrics. Now, if E, what's E? E is the permittivity, the total permittivity, and mu are the same in all directions. For example, if you take a crystal ball, made out of, let's say, the same glass as your drinking water glass is made up of. Now that glass is optically isotropic, right? Yeah, that glass is isotropic, meaning that the permittivity, the permeability would be the same in all directions. Now look, I've put epsilon here rather than epsilon naught, and mu here rather than mu naught, because I mean the total permittivity and the total permeability, right? Which is a product of the relative permittivity times the permittivity of free space, and same for the permeability. Okay. So if the permittivity is the same in all directions, then D is equal to epsilon E everywhere. So del dot D is equal to 0 is the same as del dot E is equal to 0, right? Because the right hand side was 0. Similarly, del dot D is of course still 0. Del cross E. Now, if you go back to the last slide, we saw that del cross E is minus partial B by partial T, but this is still minus partial B by partial T, so no difference there. And the fourth Maxwell equation, which in the previous slide is del cross H is partial D by partial T, that now becomes del cross B is equal to mu epsilon partial E by partial T. So we've taken the Maxwell equations inside a material, and we've said that for an isotropic material, they just reduce to these 4 equations we have here now, right? And these equations are identical to the Maxwell equations we had in vacuum with no free charges and no free currents, right? These are exactly the same equations with one important difference, and this is going to make all the difference, which is that instead of mu naught epsilon naught, we now have mu E. So instead of that, everything else is the same. So the whole mathematics is the same. And that is the beauty of working in any material as long as the free charges and free currents are 0, which is not a very bad approximation for glass or plastic or many other materials, right? So if we then solve these equations, what we expect to get is something which is exactly like the solutions we were getting before, with the only difference being that epsilon naught mu naught has been replaced by epsilon and mu, right? Not the knots. So what if you then construct the wave equation, and then if you would go about solving it, the only difference would be that, let's say if we write down the equation for the electric field, you'll probably get something like del square E is equal to 1 over V squared del 2E by del T squared, okay, which would be equal to mu, sorry, it will be equal to mu epsilon del 2E by del T squared. And the only difference between this wave equation and the wave equation we used to have was this factor, right? So extrapolated from that, you can see that when we solve them and we get our solutions, then our solutions would be such that the speed of propagation of electromagnetic waves in a linear homogeneous, when I say homogeneous, I just mean isotropic, के हर डायरेक्शन में permittivity या permeability same है, जो भी है same है, is, so V जो है that will become equal to 1 over the square root of epsilon mu, ठीक है, which should be equal to should be equal to 1 over square root of epsilon naught epsilon r. Epsilon r is the relative permittivity. It's related to basically the electric susceptibility. You can go back to your notes and check this. Mu will become equal to mu naught mu r, which is equal to we know that 1 over mu naught epsilon naught is just the speed of light in vacuum, so that's c over the square root of er mu r. So that becomes equal to c over n, where n is equal to 1 over the square root of epsilon r mu r, and n is what's called the refractive index. Now let's take a few seconds to try to understand what has happened here, because what's happened is really cool. So what we've done is that we've written down, we've taken our Maxwell equations, which are always true. We expressed them in the form of the displacement current and the H field, which we discussed a few lectures ago is easier to do because then you only have to work with free currents. Once we've done that, we've seen that for a homogeneous medium and for a medium in which there are no free charges, the Maxwell equations actually look very similar to the same Maxwell equations you have in a perfect vacuum, except that you only have to change the values of the permittivity and the permeability. And we've seen that when you construct the wave equation is also identical as we see here, with the only difference being the factors of mu and e. And so the solutions would also look very similar, but the only difference would be that the velocity, the speed of propagation of this electromagnetic wave would seem to be, inside this medium, it would seem to be less than the speed of propagation of light in vacuum. And so that would be less by what factor? Well, less by c over the square root of er mu r, and that factor we call n, and that's the refractive index. So when someone says that the refractive index of water is 1.4, what they are saying is that when light enters water, the water molecules they become polarized in such a way microscopically, right, that it acts as a dielectric, and so it gives some dielectric properties to that light, and to that medium, and so there's some displacement, so on and so forth, and whatever happens, the net result of that is that light appears to travel slower inside water. Same for glass, and that's the refractive index. It's 1 over the square root of er mu r, right? And for most materials, this number is greater than 1. But this is the physics behind it, right? I want you to understand where this is coming from, and this is all coming from when we first started talking about dipole formation under the action of an electric field, when we started talking about induced dipoles, so on and so forth, right? Um, so it's really beautiful how all of that ties up to everything we see around us in our everyday life, right? And of course, everything then follows from here: lenses, bending of light, dispersion, diffraction, everything. So just one point, which is that for most materials, so now this is just a rule of thumb. Uh, for most materials, unless you have some very special magnetic materials, for most materials, mu is approximately equal to mu naught. The relative permeability is usually a small number. So for most material, n is just approximately the square root of ER. So then we can actually take this a bit further. And so the best part is that since the Maxwell equations are essentially the same with this minor correction, all the other calculations are also pretty much the same. For example, the energy density U inside a dielectric, if you have an electromagnetic wave propagating through a dielectric, the energy density is 1/2 times epsilon E squared plus B squared over mu, right? And similarly, the Poynting vector which we denote as S would become equal to 1 over mu, not mu naught, 1 over mu times E cross B, right? So so now we know how to treat electromagnetic waves inside a dielectric, and these are a lot of materials, and we understand why materials have refractive index, and we understand it very fundamentally, all the way from Maxwell's equations to a phenomenological description of the problem. Right. So I hope that's clear. And the last topic that I wanted to discuss for this lecture is actually it's a personal favorite of mine, and I hope that you'll like it too. And it's a topic of polarization. Now, by convention, the polarization of an electromagnetic wave is the direction of the E field. Right? That's just the convention. I personally believe that the reason for this convention is that typically electric fields they interact very very readily with charges, and so a lot of the phenomena that you see, for example, if you put a polarizer or something else, then the direction of the polarizer typically interacts well with the direction of the electric part of the electromagnetic field. So I believe that's why that convention is there. But the polarization of an electromagnetic wave is the direction of the electric field. So let's try to formalize this a bit so that we understand this in a deep manner. So consider a plane wave. Another favorite of ours in this course. Now let's take a plane wave. So some E of RT is equal to some E naught. Let's say we just put whatever directional dependence in this E naught exponent of I times K dot R minus omega T, right? K, as we did last time, is 2 pi by lambda, and it's what's called the propagation vector. Now we know that light is a transverse wave. By the way, excuse me for saying light. When I say light, I just mean electromagnetic radiation. But this is true for light for electromagnetic waves of millimeter wavelength, of microwaves, radio waves, X-rays, gamma rays, you name it. This is the same physics, right? Which is another reason to love electromagnetics and optics. Light, we know that light is a transverse wave. So that basically means is that the dot product of the electric field E of RT, its dot product with the K vector must be equal to 0. ठीक है. And for the sake of our example, let's assume that light is propagating along the z-axis. Right? So if light is propagating along the z-axis, so we have a plane wave. So we have a plane wave, okay, and light is propagating along z. Now, what this necessarily implies is that this, of course, is the xy plane, and so that means that the light must be polarized. Sorry for the bad spellings there. This means that light, yeah, the EM field must be polarized in the xy plane, right? So So I mean, like I've said before, there's nothing special about the z direction. It's just convenient to pick an axis. So let's say, and for the rest of this lecture, let's just assume that light is polarized along the z direction. No matter where light is propagating along, if it's a plane wave, you can always call that direction z, right? So it doesn't really matter. So whenever that is, your electric field vector is polarized in the xy plane. And so what we can do is that we can represent the we can represent the polarization with as a linear combination of two orthogonal vectors. Right? And so what I mean when I say that is that if we have our y and x axes, and this is, let's say, this is the electric field vector in the xy, then if, for example, you have an electromagnetic plane wave, some angle theta, if you have an electromagnetic plane wave polarized along the x-axis, then you can basically write the electric field vector, as some E naught I hat plus some 0 j hat, right? Or you can express this in column vector form, in column vector format, and in column vector format you can just basically write that E is some EX 0, right? Similarly, let's say this is case 1. Similarly, in case 2, let's say you have an EM wave polarized along the y-axis, and in this case we can just write the electric field vector as 0 EY, right? So then coming back to this case, where you have a general electromagnetic vector, a general vector oriented at an angle theta, let's say with regards to the x-axis. So I'll just redraw that figure here for convenience. So if you have this is x-axis, this is y, and if you have a general electromagnetic wave, and this is the direction of the E field. Then in column vector format, we can just write this E field is some mod E cosine theta and the mod of E sine theta. So mod E cosine theta captures the component of the polarization on the x-axis, and mod E sine theta basically takes its projection on the y-axis. Okay. So this is how basically you can represent. To summarize then, in column vector format, Ex0 would be polarized along x, 0 Ey would be polarized along y, and this thing basically would be some angle theta to x-axis. And what we're writing here basically is so what this is that when you express, when you have a plane wave, when you basically express some E naught, let's say cosine of kz minus omega t, then what these column vectors are is this vector, right? So I mean, if you have light polarized along y, you'll just get a j hat because of this. If you have along x, you get an I hat because of this, and if it's at some other angle, you get this, right? So I hope it's clear what we're talking about. If it is, then I want to discuss another very cool aspect of polarization, and that's how can we get elliptically or circularly polarized light. So let's go back to let's go back to formula. So consider the following. So let's say we have a plane wave. Look, it's still a plane wave even though it'll be circularly polarized. So let's say we have a plane wave. E of rt is some E naught sub x e to the I of k dot r minus omega t I hat plus some E naught sub y e to the I of k dot r minus omega t j hat. Now we know that if E naught sub x is 0, then this is a y polarized electromagnetic wave, and if E naught sub y is 0, then we have an x polarized wave, right? And if they're both non-zero, but like, you know, it's some angle theta between them, so it's a linearly polarized wave at some angle theta. But here's where the magic happens. So if E naught sub x over E naught sub y is equal to I, where I is just the square root of -1, you know, our usual I, then what happens is that you get circular polarization. And why does that happen? Let's consider the following. So take the real part. Take the real part of the following wave. which is so let's define a new wave. So take some electric field E of RT, which is equal to some E naught sub x. Take it. Now remember this, the equation we're writing in blue, this is a new electric field different from the one we did before. Achha. So this is some new plane wave which has an E of RT equal to E naught sub x e to the I of kr minus omega t dotted with e to the I pi by 2. Okay. Plus E naught sub y e to the I of kr minus omega t j hat I hat. ठीक है. So what are we basically saying? What we're saying is that we essentially have a plane wave. We have a plane wave which is very similar to the plane wave we had before, but the difference between this plane wave and this plane wave is that in this plane wave, in the x component, we have added an additional factor of e to the I pi by 2. Why e to the I pi by 2? Because through Euler's formula, we know that e to the I pi by 2 is equal to the cosine of pi by 2, which is 0, plus iota sine of pi by 2, which is 1. This is equal to I. Okay? So I'm building towards circular polarization. So what I've done is, in the x component, I've added a factor of I. What does this do? What this does is that when we take the real part, of this E of RT, of this wave, of this electric field, what we get is that this is equal to E naught x sine of kr minus omega t I hat plus E naught y cosine of kr minus omega t j hat. Now so you might say, where did the sine come from? Well, we got a sine because if you go back to the previous slide, we had a factor of e to the I pi by 2. Now that's a phase. What happens when you add pi by 2 to cosine? You get a sine, right? And that's exactly what's happened here. So the x component is now sine of kr minus omega t. The y component is a cosine of kr omega t. So there is a 90-degree phase difference, 90-degree phase difference between the x and y components, and this is really fundamental. And what happens at the result, as a result of this, is that, and I'll write this in red, is that the E field rotates. It actually rotates, and it rotates both in time and it rotates in spatially. So I just want to point something out, that if the magnitude of Ex is equal to the magnitude of Ey, यानी कि जो x component है electric field का वो y component के बराबर है, and if Ex over Ey is equal to I, if this condition is met and this condition is met, then we get circularly polarized light. Yeah, circularly polarized EM wave. If mod Ex is not equal to mod Ey, but still the phase of Ex over EY, yeah, EX over VY is equal to some constant A times I, then light still rotates, but in this condition, I'll just separate from this, you get elliptically polarized light. So if mod Ex is equal to mod Ey and Ex over Ey gives you an I, then if I draw the X and Y axes, then what happens is that your polarization vector rotates and does a full circle. Okay? And it could either rotate left or it could rotate right, and this depends on whether Ex over Ey, whether it's equal to plus I or whether it's equal to minus I. And we'll discuss this a bit in a bit more detail in a couple of minutes. So think about this for a second. If you freeze time, okay? If you freeze time, so this is, if you freeze time, and if you have an electromagnetic wave in, let's say, I mean, this is the Z axis, right? It's propagating in Z. Then in the time that you walk, let's say, one wavelength, so if you would walk from here to here, because this difference is one wavelength, if you walk along one wavelength, okay, you will see the E field rotate by 2 pi. So the E field would rotate by 2 pi, E field would rotate by 2 pi, so on and so forth. Okay, in every lambda. Of course, it's rotating in the XY plane. Similarly, if you stand at a point, let me just write this. If you stand at one point and you let time pass, what you will see is that the E field vector at the point you're standing, when a plane wave is passing, we just need to rotate. But how fast does it rotate? It rotates at a frequency of f, where f is just basically omega over 2 pi, where omega is the angular frequency. So and in terms of time period, it rotates every 1 over f seconds. Okay, so you can imagine if you're standing and at some point and green light is passing through that point, then the electric field vector is rotating at a petahertz frequency, completely rotating at a petahertz frequency. This is mind-boggling if you think about it, right? And then if we were to let's say just express this in vector form, right? Then if E is Ex over the square root of 2 times 1 I, then what you have is a right circular wave, and if you have an E which is equal to Ey over the square root of 2 I1, what you have is a left circular wave. And what right circular means is that if these are your x and y axes, then your electric field vector rotates like that. And what left circular means is that if these are your x and y axes, and this is your electric field vector, then the vector would rotate in this direction. Okay? This is anti-clockwise. No, 1 second, let me just think about this. Yeah, this is anti-clockwise, this is clockwise. Okay, so this is anti-clockwise, this is clockwise. Now I hope this is clear, because what we've basically discussed here is that whenever you have a 90-degree phase difference between the x and y components of an electromagnetic wave, okay, then that 90-degree phase difference either leads to circular or elliptical polarization. It's circular polarization if the magnitude of the x and y components are the same. It's elliptical if the magnitudes are different. And I hope you understand कि किस चीज़ की बात हो रही है, ठीक है. ये मैग्नीट्यूड उस चीज़ का है जो कि कोसाइन से मल्टीप्लाई हो रहा होता है. And yes, the B field is also rotating because we know that the E and B fields are coupled through Maxwell equations, and so the B field is also rotating. But we classify the polarization using using the E field. Now this is a very vast topic. I hope we had a lot more time to discuss it, but I can just say that basically all LCD displays, all liquid crystal displays, let me just not use an acronym, so all use polarization properties of light to modulate their display. But understanding polarization and the optical properties of light, it's a fascinating topic, and maybe at some point we can have a detailed lecture on that. But I hope you appreciate polarization. I hope you appreciate how we solve for Maxwell equations in any general dielectric, and I hope you understand how light can transport energy, how it can transport energy in vacuum, and how it can transport energy in inside a medium. And I apologize for using light. When I say light, I mean an electromagnetic wave. Visible light typically means light between a wavelength of 400 and 700 nanometers. But you can use this terminology interchangeably. Thank you very much for your attention. Next time we'll be in lecture 19. We'll be going on to the reflection and transmission of light whenever the reflection and transmission of an electromagnetic wave whenever it hits an interface, and that would be our stepping stone into the field of optical waveguide and transmission line. So I'll see you next time. Take care.